Anybody have any questions about homework or anything? Stuff making sense, hopefully? Well, today, what we're going to talk about is going to make you take a big jump in your ability to do statics problems that you see in the world. Before we get into that, two things to look for. So there'll be like always, there'll be a daily assignment today. But also today, I'm going to post the first weekly assignment. So look for that. It'll be linked to an announcement, so you can just you can get the file straight from the announcement. And you're going to have over a week to work on it, and it's not going to take very long. But this is the first thing that I'm going to grade, really grade. I think I have it listed as being due Tuesday, what would that be, the 20th, something like that. Okay. You can talk to each other about it, but you need to submit your own work, so people can help you understand how to do it, but you need to do it by yourself and turn in what you do by yourself. And don't put it on Chegg. All right, so today we're going to talk about 2D joints. Yeah. Mm-hmm. Yeah. Mm-hmm. You know what, actually, can we just talk about it after class? I'm going to get into this so I make sure I get far enough to do the problems and stuff, and then I'd be happy to talk to you about that after class. Okay, so the idea with joints is, so joints are just connections between bodies. We've talked about things as joints before with particles. And the way to think about joints is in terms of the motions that they restrict. Okay, so all a joint can do is limit the motions that an object can have. If you connect two objects together, you're limiting the motions that one has relative to the one that you're, considering fixed or whatever. And understanding in what way joints limit motions is the way to understand mathematically how to treat joints. That's in 2D and 3D and with particles. So joints limit motions, and how a joint limits motion tells you how to treat it mathematically. Okay, so in 2D, every object, before you put any restraints on it, has 3 what are called degrees of freedom. So every object has 3 degrees of freedom. Before you limit let's say limit its motion through contact with other bodies. These 3 degrees of freedom are motion along one line, and by motion, I guess you can also think of it as translation, maybe is a little more specific, translation along a line. Translation along a perpendicular line. And rotation. Notice that those 3 correspond to the 3 equations we get from Newton's second law and the moment equation. In 2D, you have the x and y components of Newton's second law, and then you have the z component of the moment equation, okay? And that's not, I mean, that relationship has to be. Let me show you, just illustrate. So say this thing sliding, moving along the table is a 2-dimensional object, okay? Like we're just looking at it from above. So once you choose your coordinate system, this thing can translate along your x-axis, whatever direction you choose as x. It can translate along your y-axis. And so that means it can translate anywhere, as a combination of those 2. And then it can rotate in the plane, which is really a rotation about an axis that's perpendicular, okay? To limit these motions, to restrict these motions, these motions or these degrees of freedom would require so to restrict the translation along a line, you'd have to apply a force along that line. To restrict the translation along the perpendicular line would require applying a force along that perpendicular line. And to restrict the rotation would require a couple. And that's all we're going to see from these joints. These joints just apply different combinations of perpendicular forces, forces in the plane, and couples with an axis perpendicular to the plane. Okay, and which one of those they apply is just totally determined by, well, does this joint let this thing rotate? Does this joint let this thing move in this direction perpendicular to it? Okay, and so if you think about it this way, you can always, whether you know the rules for that joint, whether you memorized them or not, you can always figure out what kind of loads a joint applies. And so I'm just going to go through the joints. Let's see, how many do we have? 1, 2, 3, 4, 5, 6 total joints. And I'm just going to do them in order of how many of these loads they apply. So I'm going to break it into categories that are just based on how many of these loads they apply. And if a load is applied, then that introduces, each load that's applied introduces one variable into your Newton's equations. So I'll call the first one category 1. All of these apply a force in a known direction. Since we know the direction of the force, but we don't know the magnitude or the sign, this introduces one variable into the governing equations. Okay, so the first one of these joints, and actually let me, before I go into that, let me try to give you one more little sort of intuitive idea of what we're going to be doing here. So I talked about that thing, whatever it is, that remote control thing, sliding around and rotating around on the table. So now let's think about what happens for something that isn't free to rotate, okay? Something that's connected by a joint, and how we're going to analyze joints. So now the plane of motion is perpendicular to the one I showed you before. It's not sliding around on the table. This thing is moving in a plane like this, like you're watching TV. But what we're going to do with every one of these joints is we're going to think one by one. Does this joint connection allow the body that we're looking at to move freely along any axis, any perpendicular axis, and then does it allow it to rotate? Okay, and that's what we're going to do just one by one. So, okay, first of all, is there any, if this is the body, the top one, okay, this is what we're drawing a free body diagram of. Connected to this joint, is this thing free to translate along any line? You know, and there's no line where I can hold on to the joint and translate this thing around, right? So it restricts motion along any X you choose and any perpendicular line, any Y you choose, okay? So that means it's going to apply an X component and a Y component of force, okay? So we know to start with that there's going to be two variables introduced, the X and Y components of force. And now let's think about the rotation. Is it free to rotate? Yeah, that it can do. So this joint isn't going to apply any couple to it, okay? And that's the way we're going to think about each one of these things. Yeah.
The joint does apply a force to
If there was no friction in it, it doesn't. I mean, this one has friction in it.
Okay, so we're doing with no friction.
Yeah. You have a question, Laura?
So you're saying, like, based on the 3 that you said to restrict the motions, there's only the first 2 that are working on it.
Exactly. Yep. Yes.
So, like, how do we define it not being able to move in X and Y directions? Like, the center of mass is technically.
Yeah. So, but think about where it's always going to be where that joint is. The translations. The question is, does that joint restrict the motion at the contact point? Yes, exactly. That's a good point. Yeah, because obviously, yeah, the center of mass and any other point is moving as you rotate it. So think about that connection point. Okay, so the first one of these is contact without friction. We've already seen this with particles. And so if this is your rigid body, and it makes contact without friction. Let's say that this is body 1 and this is body 2, okay? It's always going to apply a force vector to your chosen body that's toward the chosen body and perpendicular to the surface of contact. So a free body diagram, or a part of a free body diagram of body 1 would look like this. Notice that, so if this is the surface of contact, then the force is perpendicular to it. And a free body diagram of body 2 so say we consider breaking off a chunk of that, whatever it is, the force would be opposite like that. And these two forces, I'll just give them the name R for reaction force. That's a Newton's third law here, so those have to have the same magnitude. Now, some of these forces we're going to talk about are going to allow forces in both directions. Some are only going to allow a force in one direction. So if you get like a negative value, you know something went wrong. This force, it can push this contact, but it can't pull. So if you ever do this and get a negative value for R, something went wrong. The something could be that joint just isn't going to work in the setting that you have it set up for, or it could be that a calculation went wrong. But you want to notice that R must be positive. The second joint in this category 1 that introduces one variable is a roller. And this can be drawn two ways. Sometimes you'll see it drawn just as like a ball between the two objects. And sometimes you'll see it drawn as like a roller skate. So those mean the same thing. And I'll call this body 1 and this body 2 again. To draw a free body diagram of body 1, again, it's this force is perpendicular to the surface. So if that's the surface of contact, the force is that direction. And for the second one, again, it's a Newton's third law pair. So this force is equal and opposite. So a roller and a frictionless contact, they apply exactly the same forces. And again, this roller, like if you try to make a roller pull on an object, it's just going to pop up off the surface. So again, just like with frictionless contact, this R value has to be positive. And then the third one in this category is a pin in slot joint. And it looks like this. You have one body that has a slot in it and a pin that goes through the body, that goes through both of the bodies, can slide in that slot. Okay. So if we think about this, I didn't do this with the first two, but think about this in terms of the degrees of freedom that are restricted. So is there a line along which that pin can translate? Yeah, it can slide along that slot. So let's call that the x-axis or whatever. That there's no force applied along the x-axis. Okay. Can it translate perpendicular to that slot? That pin can't translate, right? It bumps into the two sides of the slot. So the motion is restricted that way. So there is going to be a force component perpendicular to that slot. And then third, can this thing rotate? Yeah, it can rotate fine around that pin. So all we have is a force acting perpendicular to that slot. So this is body one, this is body two. So free body diagram of body one. If this is the direction of the slot, the force has to be perpendicular to that. And then if you're drawing a free body diagram of the other one, it's a Newton's third law pair, so it has to be perpendicular to the first one. There's something different about this than the other two. Notice that no matter which way you try to move body one along that perpendicular axis, its motion is restricted. So in this case, that R can be positive or negative. And so it doesn't matter which way you choose when you draw this in a free body diagram and when you put it into your equations, because it can come out positive or negative anyways. So R can be positive or negative. And if you're designing some kind of system where you need your joint to be able to apply a force in either one of two directions, then you'd want to use a pin and slot joint rather than a roller or a frictionless contact.
Another context about friction.
Mm-hmm.
Since it's in Newton's third law of air, wouldn't one of them be positive?
No, because you would draw them in this direction. So think of that as just a variable that represents the magnitude in that direction. Okay, and so If you drew the arrows in the same direction, then yes.
Okay.
Yeah.
So what about the x-axis?
The what?
What about the ends then on the x-axis?
Well, yeah, I mean, this is static, so you're either at the ends or you're not when you start the motion, you know what I mean? So if you're at the ends, then it's not a pin and slot joint in your application, you know, it's a pin joint or something. Okay, so now the next joint category 2. How many joint categories are there going to be? 100? 3, yes, exactly, 3. So you can only introduce 1, 2, or 3 variables into these equations in 2D. (3D) is going to be more time consuming to go through all these, because how many of these categories can you have for a 3D joint? 6, exactly, because there's 6 degrees of freedom. 3 translational and 3 components of rotation. So each of these, the joint applies a force with an unknown direction or a full vector of forces. So these 2 joints each introduce 2 variables into Newton's laws. Okay, the first one of these is the one that I have the model of there, a pin joint. This is the same thing as a hinge. And drawn something like that, you can just see the pin that's connecting the 2 bodies. A free body diagram of body 1 looks like this. And we'll call the force vector the force on 1 by 2. And it's going to be really important when we start getting into connections of lots of bodies with lots of joints that you get used to like careful use of that subscript notation. And a free body diagram of body 2. I'm going to keep drawing the component directions in the direction of the coordinate axes, but the variable now is going to be the force on 2 by 1, and Newton's third law says that's equal to negative F(1)(2). If you're like, I don't have time for this, I got, important stuff to do. I don't have time to learn about 6 2D joints. This is the one that's going to be 75% or more of the things you do in 2D. So know this one. And then the second in this category, the last one in this category, is contact with friction. So friction contact. So really, it doesn't look any different than contact without friction. The problem just has to tell you whether there's friction or not. If that's body 1 and that's body 2, a free body diagram of body 1. Looks like this. And a free body diagram of body 2. Looks like this with a force on 2 by 1. And then for our purposes, since we want to use as few variables as possible, the important thing is noticing that that's negative force on 1 by 2. Since our coordinate system is not always aligned, I mean, most of the time it won't be aligned with that surface of contact, there's not really an easy way to say, like, okay, something has to be positive or something has to be negative. But you can imagine that there's a way to check to make sure, because this friction force can apply a force parallel to that surface, but the normal force can't apply a pulling force. So you could use dot product or whatever to figure out if this thing is saying that you need to apply a pulling force, because that wouldn't work with it. But if you have a little time and are interested, think about that and see how you would do that. But that's not something you're going to really, I'm not going to make you do that in this class. Okay, and then the last category, joint category 3. This applies a full force vector and a couple to the body. Let's say to the chosen body. And that means it introduces 3 variables into Newton's laws. Well, that means that this thing is just held rigidly in place by the other object. And so this is called a fixed joint or a weld joint. And it's usually just drawn something like this. Sometimes you see it drawn with like a dovetail kind of joint. Call that body 1 and this body 2. Then a free body diagram of 1. Looks like this, F1, 2. And then, so that's the force that says there's no motion between the two. And then there's also a couple. And you can call that M1, 2. and a free body diagram of body 2. There's a force vector that's the force on 2 by 1, and that's equal to negative F on 1 by 2. And then there's the couple M on 2 by 1, which is negative M on 1 by 2. And so whenever you see any of these joints, all you do is put the loads as they're shown in these free body diagrams into your free body diagram, and then you do the calculations to get those variable values using Newton's laws. So I said there's a connection between the number of degrees of freedom that a joint can restrict and the number of Newton's laws that are available, right? There's 3 of each in 2 dimensions. So since there's only 3 Newton's law equations for a rigid body, in order to be able to calculate the loads in a joint using a rigid body, how many total variables can you have? You have 3 equations. How many variables can you find? 3. Yep. And if you have 4, it doesn't matter if you're great at statics or terrible at statics. There's nothing you can do. So if you have a single rigid body, you can have 1 fixed joint, or you can have 1 pin joint and 1 frictionless contact, or you can have 1 roller and 2 frictionless contacts, but the number of variables you get can't add up to more than 3, or you can't solve it. That's for a single rigid body, which is what we're doing right now. We'll see that you can have tons of joints if you have tons of rigid bodies, because you get Newton's laws for each one of those rigid bodies, But if you have a single body, all you can have is 3 variables. Okay, let's do an example problem, and I'll show you how this works. So let's say we have a pin joint at the middle of this beam, and a roller at the end of this beam, and a downward force of, let's say, 500 newtons. And let's do a horizontal one too. 1,000 Newton horizontal force. And let's say that this beam is 3 meters long and 50 kilograms. What are the external loads on this beam? Well, the first step is always to draw a free body diagram. So, free body diagram. So there's the outline with no external anything. There's a weight force acting at the center of the object. 50 kilograms times 9.81 gives you a downward force of 490.5. Then there's these two given external loads of 500 and 1,000. Oh, you know what? Let me put one more thing in just so you see it. Let's pretend I did this at the start. So let's put a couple in of 300 Newton meters. That didn't change the number of variables. The only variables are come from the two joints. Everything else is known. You know what I mean? So we're going to get two variables from the pin joint and one from that roller. Okay, so now we have the weight force and we have those three known forces. Now we have the pin joint. And I'm just going to call that R vector, since we're never going to draw a free body diagram of the ground. There's no need to use the double subscript notation. And then the last force is from the roller. It's toward the chosen body, perpendicular to the surface of contact, so it's straight down, and I'll call that F. So the variables we're trying to solve for are F, Rx, and Ry. That's three variables, and we should be able to solve it. So now I'm going to write out a row force moment table. We have to choose what our about point is going to be. I'm going to put the about point here at the center. And the reason that is going to simplify the math a little bit, conceptually it doesn't change anything, but it simplifies the math a little bit because that weight force acts straight through the about point, which means it produces zero moment. And the pin joint force acts right at that about point, so that's not going to produce any moment. Okay, so it's going to simplify our moment equation a little bit. If you didn't do this, this would still be, perfectly solvable. You'd still get the same answer. Okay, so first, let's do I'm going to treat you can do them as separate forces. I'm going to treat the 500 and the 1,000 as a single force vector since they're acting at the same point. So I'm going to call this a vector of 1,000 negative 500. The vector from the about point to where those forces are applied is, what did I say this was, 3 meters? 3 meters. So it's 1.5 meters from the center of the beam to where that force vector is applied. So 1.50. The force vector is 1,500. The cross product of rho and F is positive 750. And remember, I'm writing that as a scalar, but that's a Z component. Anybody have any questions about that? Yeah, this 500 should be negative, and so the moment should be negative. Thank you. And you can also make sense out of that because this is the about point. And if you had a hinge here and applied a downward force at the end, it would rotate it clockwise, which is negative. Yep, exactly. Now let's do the couple. So the 300 Newton meter couple. For couples, we don't care about rho or F. This is a clockwise moment, so that's a negative 300. Now we can do the weight force. What's the rho vector from the about point to where that weight force is applied? Yep, 0, 0. The force is 0, negative 490.5. And so the cross product is 0. This and the force applied by the pin joint are the reason I put the about point there, because we'll get those zeros in the moment. Now let's do that force R, the pin joint force. The rho vector again is 0. The force is Rx, Ry. Cross product is 0. So now we got 1, 2, 3, 4, 1, 2, 3, 4. So the only thing we have left is this force F applied by the roller. What's the rho vector for the force F? Yep, perfect. Negative 1.50. The force vector is 0, negative F. So the cross product is positive 1.5 F. And now we have this complete table. If we add up all those forces in the, everything in the force column, set that equal to 0, that's Newton's second law. Add up everything in the moment column, set that equal to 0, that's the the moment equation. So Newton's second law says, so for the x component, we have Rx plus 1,000 is equal to 0. I'm going to write that as Rx is equal to negative 1,000. The second equation says Ry minus F minus 490.5 minus 500 is equal to 0. I'm going to move all the constants to the other side again. So we have Ry minus F is equal to 990.5. And then the third equation, and if you want to write these out, that's perfectly fine. I'm just skipping that one step. But write it all out as vectors or whatever. I always do everything I can to try to make sure that you don't feel like you're racing against the clock in tests or anything. So if it helps you to visualize it, to write it out, for sure do it. And then the third one says 1.5 minus 300 minus 750 is equal to 0, or 1.5 F is equal to positive 1050. And now you could solve this with reduced row echelon form, but this one's pretty easy to just do by substitution. So we have F is equal to, what's 1050 divided by 1.5? I should have known that. 700 newtons for F, and then R is negative 1,000 for X, and negative 290.5. Is that right?
Maybe adding.
R uh, 700. Oh, yeah. So, what did you say? 1690, right? 0.5. Yes. Okay. So that F value needs to come out positive because it's a roller, and it did. So that's good. The pin joint can come out positive or negative. And so the last thing we're supposed to do, it said, was to write this all in a free body diagram. So you have those two forces. You have the weight force. You have the couple. Those haven't changed, so I'm going to just skip writing the numbers. But then you have the force vector here that's negative 1,000, positive 1690.5. And then you have the force vector acting down of 700 newtons.
And why is it not moving?
Because if you plug those values back into, back into Newton's laws, you'd see that they all add up to 0. Those are the loads that are required for it not to be moving.
So, like, what stops it from moving? Like in this scenario,
Okay, well, you can imagine if that roller wasn't there, if there was no contact there, the 300 Newton meter force and the 500 Newton force would just make it spin. But it's kept from spinning by that roller blocking it. And it would translate to the right if that pin joint wasn't there.
Oh, I was looking at it, I was thinking the 1,000 was down. And, okay.
Okay, yeah. So those are the forces that are required for it to be in static equilibrium, or the loads. Yeah.
When writing the road vectors, are we treating this beam as
Yes, we are, but remember that you can move any force anywhere along its line of action without changing the value. So you can imagine when that F was applied in the center of the beam, you can imagine the 500 is applied in the center, and then it doesn't come into it anyways. Any other questions? Okay, so I'll give you a daily assignment for today. I also am giving you the weekly assignment that you have like 10 days or something to work on. So, all right, see you on Monday.